Very good. Can you hear me? Well, great. Thank you so much. So thank you so much to all the organizers of this session. I know that there are lots of people, a lot of people have been working on this for many days, many weeks actually. I heard that there were lots of last minute changes to be able to put together this fantastic venue. So I really want to appreciate everyone who worked on this. I know there's a lot of work behind this. And also thank you so much as well to Laura's and Matt for also being there with me and also all the team at Yale who's been preparing for this in the background. We're coming to you with a lot of stuff, and it's been years and years of work from many, many people. So including actually people like you who contributed and give us feedback and ideas. So I want to thank everybody involved with this. I'm going to start with a little bit of work from my own group, show you a little bit what we do. Some of the concepts that I'm going to allude to in this talk, actually, we're going to talk about them a little bit more in depth, as the week proceeds. So stay tuned for some more if you need to. So I just wanted to give you a little bit of a sense of where I'm coming from. I'm coming from Montreal. So this is the I'm not sure you actually are able to. Yeah, it doesn't work as well, right? So I'm coming from Montreal, which is located around here. So it's if you know where New York is, it's a little bit further north, but on the same longitude. It's a really nice place. In the summer, it's very warm. It looks like this. Right now, it's about 10 to 20 degrees, and it's very cool and nice. And then in the winter, it becomes very, very cold, and there's lots of snow. And we're really blessed at McGill to have beautiful facility in the downtown area while at the same time benefiting from these really nice legacy buildings that you can see here. Also, McGill is in Canada, and in Canada we are trying to develop an understanding and respect for Indigenous communities. And what we do when we start any event is to acknowledge the land of where McGill sits. And McGill in particular was a place where Indigenous people came and gathered, especially the Haudenosaunee and Anishinaabe nations. So it's important for us to be mindful of this legacy and honor people who inhabited the land before us. This made me think as well about looking up what was the situation in Indonesia about Indigenous communities. And I was really interesting to talk to my colleague here this morning about building this map, right? Because you've been involved in some of that work. So this is really fun. And this is a really interesting thing that you've been doing in Indonesia in the past few years. So this is 2021, where you started to map out different Indigenous communities and recognizing the land there in Indonesia. So I just wanted to share that with you, and of course learn more about it, because I'm sure you can teach me a lot about that. So my own background, I'm coming from France originally. I was born and raised there, and I was studying catalysis and inorganic chemistry. I spent some time in St. Andrews universities as well as a undergrad researcher doing some research there. And then I started to work more with nanoparticles at the end of my PhD. And then I started to be introduced to green chemistry when I started my postdoc at Yale. And after that, I started my independent research at McGill, and this is where I added biomass chemistry, mechanochemistry to the mix of things that we're doing. And we're really trying to encompass all of these concepts and ideas in our research these days. So this makes for a really fun subjectivity, and you're going to see some of this today. The Train the Facilitator program is really dear to me because I'm very proud to say that I was there for the very first that was given in 2018 in South Africa. Sorry, it's sort of hidden there. It was 2018. So this program has been going on for many years now. And this is me with a bunch of people in Pretoria in South Africa, where we organized the first event that day. And also this year we you heard that we're going in multiple countries. In particular we went to Ukraine, and we've taught this workshop virtually. Unfortunately, we're not able to join people in real because of the war there, unfortunately. But it's a really fantastic experience talking to people over there and seeing the determination of these people. They're fighting a war, but at the same time, really trying to develop better ways, better processes locally for their community. So it was really, really impressive. So my group is working at the interface of biomass, synthesis and catalysis, and also trying to do metrics and assessment, which is really important in green chemistry, and we will definitely touch on that sometime this week. In particular, today I'm going to talk about biomass here, and I'm going to talk about synthesis and catalysis in the context of something called mechanochemistry. So I'll talk a little bit about mechanochemistry today. I'll talk a little bit about mechanochemistry tomorrow. So if you don't know what this is, it's okay, stay tuned. You'll learn more about this over the course of this. So one of the big area of development in green chemistry is this concept of biomass. We should use more biomass to try to have to use less petrochemicals, which can emit a lot of carbon. So people are really turning to this, and I think Indonesia is an incredibly interesting playground to discuss this question, because you guys have an oil industry, and also you have absolutely beautiful forests up there that people might want to use as a source of biomass, right? So this is some of one of your beautiful national park in Kalimantan. You could see the beautiful forest and also incredible biodiversity, including the orangutan monkey. And of course, another source of biomass is also to use agricultural land to grow biomass and use it for different chemicals or end uses. So you can see here some palm oil industry. This is from Indonesia. So obviously there used to be forest there. Now we have palm oil. Palm oil is used for chemical production as well as for food production. So there are issues here around what are we using for food? What are we using for chemistry? Are we okay to destroy the forest? So there are really some really interesting debates that are both really important from a green chemistry perspective, and also really important from the perspective of social problems and also philosophical problems, right? Is it the right thing to do? This is the question to ask. So my own take on this, and we're going to talk more about this as the week goes on, is that these are really complicated, and maybe there are other alternative routes to using biomass, but doing it in a way where we don't have these big conflicts. You know, are we doing the right thing to use the forest? Are we doing the right thing to use the land that we could use with? And that's using another source of biomass, that is biomass waste, right? So if I use biomass waste now, I don't have to worry about using up forest or using up land that I can for food. I have waste there to use for me, and it's there anyway, right? Whether I use it or not. If I don't use it, actually, it's going to cause a ton of problems. It's estimated that about a third of all the food that we produce every year in the world is actually wasted. That's not even taking into account what is not, the residues that we have from agriculture. This is just the food that goes bad as we're producing it, transporting it around, deciding that the apple is too small or a little bit bruised. This is what I'm talking about here. So there's huge potential in using biomass waste and biomass residues from the perspective of using biomass. So this is something that also has been tied to the concept of circular economy. We heard about this a little bit this morning. We heard about this in the different speeches of your ministers this morning as well. Circular, going from linear to circular. Waste is super important there. Waste is what you can use as a resource if you want to make your economy truly circular. One of the specific areas that I'm interested in myself is fisheries waste. And fisheries is an industry that is continuously growing, right? We all know that as we are using more and more, as we're fishing more and more for food, we're also increasing the waste that is generated from that. So one of the concepts that has emerged from this is this concept of blue bioeconomy or blue biomass. What is it? It's this idea of using this waste from biomass specifically coming from fisheries. So fisheries, you can fish in rivers, you can fish in oceans, you can do aquaculture, you can do fishing. All of these things will count as blue biomes. Use that for new chemistries, right? So typically all that you do is you use these things, you make food or non-food products. For instance, collagen that's extracted from fish is one of the non-food products. These particular things is what you want to do. So right now we're doing that. But what we're not doing enough of is taking the waste from these processes, which often accounts for a lot of what we have fished, and trying to use them as a resource instead. So in my group, we're particularly interested in one type of blue biomass, and it's the crustacean biomass. So in crustaceans, when you take off the meat and you eat the meat of this delicious crab here, right? You have delicious cuisine around crustacean here, right? I've eaten some delicious prawns yesterday, so definitely in that realm. When you take the waste from crustaceans, you can actually extract really interesting molecules like chitin and chitosan, and we're going to focus a lot about that. There's also proteins, minerals, and pigments that you can use, all of which are interesting. The one that has the biggest volume and at the same time good commercial value is actually chitin chitosan. But for the rest of the talk, I'm going to really focus on this particular molecule, and it has application in a bunch of different areas that are highlighted here: cosmetics, nutraceutics, and so on. You can see it here from another angle. Chitosan is this really interesting molecule that looks like cellulose, except it has an amine functionality in two of these positions there. And this particular biopolymer you can extract from nature, from this crustacean waste in particular, but you can also extract it from mushrooms. And what's interesting is that depending on the molecular weights, you can hit different types of applications, from using them in nutraceutics, biomedical application, for making smart fertilizers, fibers that are antibacterial, and also for water treatment. Water treatment is the big area where this is used right now, because it can replace some petro-based polymers that are flocculants, and these ones are non-biodegradable. So using chitosan is really interesting to turn this into more biodegradable materials. So we're also interested in crustacean waste because we make a ton of it. Literally, we make tons of it globally. So it's estimated that between 6 and 8 million tons of crustacean waste is not used for anything at all every year. And in fact, this number is probably an underestimation because it's an older number. So I would anticipate that it's probably closer to 10 million and more. And in Canada, we have different regions that we call provinces. My own province is called Quebec, where Montreal is. And in just my province, we consider that we produce 40,000 tons of waste crab, shrimp, and lobster just in my province. So this is really huge for us. I mean, our province only has 8 million people. So it's really a big amount that we should valorize. Right now, in Quebec, in Canada, we're not doing anything with it. That's a big problem because we have a lot of it and we don't know what to do with it. So it's a shame because we could make money out of this waste. I showed you that chitosan was actually a really interesting polymer. We should do something about it. We should make money out of this. It would bring extra revenues to our fishermen. This is important. We have a molecule here that contains nitrogen, which is super important because nitrogen is life. So it appears in a lot of the pharmaceutical compounds that we take. It's really linked to really high value. So we should definitely extract these materials. And even more importantly, I would say, if we do something with this waste, we're going to have less waste to deal with, which is causing a big environmental burden. Right now, people tend to dump their crab shells onto the sea or in landfills, which is causing bad odors, unwanted biological activities. I mean, it's really not good. So we don't have a big solution other than doing it. You can compost. Some people do that, but it is quite resource intensive and you make a low value material. So what we want to do, and many of us in this field, is to create what's called a shell biorefinery. So taking the shell turning it into useful molecules and selling them for profit. So, okay, I've told you all of this, and now you're going to be, okay, Audrey, this is a done deal. It's easy. You have waste. You could turn it into something useful. Why is that no one is doing it? What? Right? I mean, it makes sense. Makes sense to do it. The reason why it doesn't work is because the process for doing that is actually quite complicated and actually costly. So people don't have, if people do it, it's going to cost them too much money to get the material, and selling it is not going to happen for a profit. And here is why. What you have to do here is you have a complex material. This is the crustacean shell. It's composed of several components, and what you want to do is extract the one of interest to you, specifically chitin and then chitosan. So if I walk you through the process, we start with this material, which is composed of a mixture of chitin, proteins, and minerals here in purple. What you have to do is first demineralize, then deproteinize to get into chitin. This is about 30% of what you had at the beginning when you do that process, 30 to 20%. And then once you have your chitin, you need to change this, the chemistry of this molecule here from an amide here to an amine to go to chitosan. And the reason why you want to do this is that there are many more applications and higher end applications for chitosan than there is for chitin. And that's because chitin doesn't have very good solubility. Chitosan does have good solubility, especially in acidic environments. So that's the way you would do this. So you have several processes to go through. And more importantly, these processes are very wasteful. They are happening under nice, nasty conditions. You use corrosive, viscous liquids. You have to heat up. And that's bad, right? You don't want to, expose people to these conditions. But actually, that's not the reason why plants were shut down. There used to be plants in Canada that were shut down about 2 decades ago. That's because it costs too much money to handle the water effluents coming out of this process. So when you wash at the end your product, you create water effluents, and it just costs too much money, and people shut down plants because of that. So this is a great example, actually, of what you need to do when you want to do a green innovation. People in green chemistry will tell you water is a wonderful solvent. You need to do all chemistries in water. This chemistry happens in water, right? But it's not good enough because you generate too much dirty water at the end of it, and the process of cleaning water is super expensive, actually. So so this is an example of where you turn a good idea into something that starts to be a problem, and where you need to revisit your concept and not say water is bad. Water is a good solvent, but maybe you need to do more. Maybe now you need to use less water. Maybe this should be your goal. And this is where we came in, because in my group, we work on a technique called mechanochemistry. So what is mechanochemistry? Mechanochemistry is when you use mechanical force as the way to drive the reaction. So all of you've done some chemistry in your life, right? I'm sure. And what you typically do is when you want reactions to go forward, you heat up the reaction. So you turn up your hot plates, heat up your solution, and a reaction goes. Well, in mechanochemistry, what we do is we use mechanical force as the way to drive the reaction. So the way you do this is you use typically mortar and pestle, planetary mills, or vibrational mills that you can see here. And by using that, you're delivering your energy this time in using mechanical force as opposed to heating. But the second advantage for you is that you don't need a solvent now. You can work in a solid phase, right? Because in order to deliver your mechanical force, it's actually much more efficient to work in a solid phase and in liquid phase. So it's really interesting to see that actually mechanochemistry has gone on for millennia. And the first written account of any chemical transformation actually was done by Theophrastus in the 4th century before Christ, and it was a mechanochemical process. It's really interesting. It was the production of mercury from cinnabar, and it was done in the solid phase by mechanochemistry in the modern pestle. After that, it was forgotten. And it's only, I would say, in the last 2 decades that people are rediscovering chemistry and now finding that it can solve problems. And mechanochemistry is really well suited to the question of biomass because biomass, typically, they're not very soluble in many things. So they are a natural candidate for working in a solid phase condition. Also, they're often complex mixtures, which means that you're going to have to do separations and extractions and things that, in fact, you're trying to separate a complex mixture that is solid in nature. So working in a solid phase is actually an advantage for you to do the separation. And finally, mechanochemistry helps reducing solvent use, which is one of the things that you want to do. It's going to give you benefits in terms of reducing your overall waste for the process. It's going to mean that you need less resource in terms of solvents. Solvents are often problematic. We know that they can generate accidents, fires. So it fixes a lot of principles of green chemistry to use mechanochemistry. And for us, remember, we're trying to reduce the quality of water. Mechanochemistry was the way to go. So we looked a bit in the literature. There was this nice precedent from my colleagues, Ning Yan in Singapore, not far from here, is really a big person in this field. I really admire his work. And he had developed an initial process in which he takes mechanochemistry to go from chitin to chitosan, although he's also breaking up the chitosan into low molecular weight chitosan. And he pursued this work with another one of my colleagues in Canada, Frank Curtin, and went all the way to monomers of N-alkylglucosamine, which is a really interesting way to make these materials that have great value, especially of nutraceutics. But one of the issues with this is that you're making some low molecular weight chitosan, and a lot of applications require higher molecular weights than this. So we thought maybe we could revisit this work and try to preserve the chain length, try to preserve the polymer without breaking it down by using a combination of mechanochemistry and aging. So what we do in this process is we take chitin, we mill it for some time to make it amorphous, and then we mix it for a very short period of time mechanochemically with sodium hydroxide, and then we let it age on the high humidity for several days. And when we do that, we produce chitosan with really high degree of deacetylation, which is degree of purity of chitosan. And at the same time, preserve the molecular weight so that we make a chitosan that can now open a lot of the applications that I showed you earlier. And we demonstrated that we could do that with different sources, from shrimp, lobster, crabs, but also insects, which is really interesting. We haven't worked on fungi. I mentioned that earlier, but it's something we want to do. But more importantly, we really pressed upon the point that I said earlier. We demonstrated that we really reduce the quantity of water we produce. This is really important. And we do this by almost an order of magnitude. So this is big. And people now in the industry tells us, oh, that's a deal breaker for us. This is interesting for us to get there because this was definitely our problem. Along the way, we also reduce again by about an order of magnitude the quantity of chemicals that we need for this. We use less energy because a lot of our process happens via aging, so we just need to wait for stuff to happen. We heat a little bit, but not too much. And also, and an additional benefit is that now we don't manipulate these viscous liquids anymore. We have a much safer operations. For full disclosure, we are manipulating a powder of sodium hydroxide, so we need to use masks because it creates a little bit of powder when we fit around. We've also adapted our process now in a larger scale to make sure that it's safe for operators to use this, but it is much easier than handling the hot viscous liquids we're using. So we're really happy about this. We had managed to find a way to go from chitin to chitosan here in what we believe is a much greener method. But you still had this question of how do we get from the crustacean shell to the chitin? And how do you do it by mechanochemistry as well? Because if you build a plant where one step is in mechanochemistry, it's much better to have the whole thing happening with similar kinds of machines and understanding of similar kinds of machines and processes. So in order to do that, we had to find some crustacean shells to work with. And they came to us in a very unusual way. So when we had made this first discovery I mentioned about the um, deacetylation of chitin, we got a phone call from Gabrielle here, who is a ranger in Parks, Canada. So she's taking care of a natural park in Canada, in Nova Scotia, in Kejimkujik here. So this is the Atlantic Ocean here. And this is the east coast of Canada. And you have Kejimkujik here. And in this park, they had a big problem. This problem is that they had an invasion of invasive crabs. These guys here. See? These are green crabs. They're invasive species that started to populate the East Coast in Canada, in the US, and now even the West Coast of North America. And these guys are extremely voracious. They start to destroy eelgrasses in the environment and really kill the ecosystems locally, because the eelgrass is essential for the growth of natural species locally. So what they developed is a method by which they trap very selectively these green crabs with these cages here. Chris is holding. And during the summer season, every day they pick up the crabs, and they've removed enough crabs now that they have restored significant part of their ecosystem. So that was a really nice story of how to get rid of invasive species like that. But their problem now is that they have a ton of these crabs, and they're like, what are we going to do with it? What can you help us? So we said, sure. We actually want to start to do extraction of chitin from crustacean shells. So it's fantastic. We're going to use your material as our study material. So we started from the green crab here. Again, this is proteins, minerals, and chitin bundled together. And we demonstrated that we could use a short milling with organic acids to extract the chitin here. And we use different solid acids. We found that malic acid was the one that functioned the best. With malic acid, we could extract about 16% of the chitin. In green crab, we start from 20-25%. So actually, this is a good number. If we compare it as well with the purity, which is expressed here in terms of hash content. And again, we have some great benefits in terms of process mass intensity. This is a green metric showing that we're, again, using far less chemical than the traditional methods or the enzymatic method. And we also use far less energy in the process, because even though we mill, it's only for 30 minutes. So it's really great. So we have actually these two discoveries. We patented them. The first one is now licensed. We're working with a startup company called L'Eau Rouge de la Côte Nord and Marc Fafard. And what they're doing is that they're trying to work with fishermen to develop processes for valorizing their waste. So they're really interested in what we're doing, and they partnered with us. So just to give you a sense of scale here, so this is the east part of Canada. This is the province of Quebec here. Montreal is here. If you drive from Montreal to the north here for about 10 hours, you will find Bétrimité, Sept-Îles, and Langon. These are harbors where they have big activity in fishing crustaceans, lobster, crabs, and shrimps. And for crabs in particular, this is the quantity of waste that they generate each of these three harbors. So this is really big. We're talking about big numbers. So they're interested in trying to see if they can build a plant to do what we deliver over there. And just for the sense of geography here, the parks in Nova Scotia was here, right? So this is giving you a little bit of geography of East Canada here. So with Justine and Hamdam, we've been working on helping develop a scale-up, which we did at a tech transfer company called CDBQ. So this is the reactor that we're using for our process. We've demonstrated that we could go to 10 kilograms for the acetylation, and we are waiting for more funding from the government. So we got a lot of funding from the government. You can see the partners over there. And we're waiting for the second tranche to now work on the process of extraction of chitin. And we hope that we could then, after that, try to fundraise to build a real pilot plant to make it work. So that's really exciting for us to play with that. So I've been telling you about the story about how you can use crustacean shells, chitin, chitosan. But one thing that's really interesting about these materials is that, and this is going to this concept of biomimicry that we're going to talk about later, is that these materials are not just polymers. They also have structure and hierarchy coming from the way they are in nature. And researchers have tried to take advantage of that for many years now to try to see if they can make advanced materials out of that. So chitin in particular is a material that is nanostructured, which means that at the nano level, they have crystallinity that you can actually harvest. Oh, I'm sorry. I just needed to tell you about something first. Sorry about that. Another thing that we did from this is to try to see if we could make even better chitosan. So we have developed a mechanochemical method for depolymerizing chitosan at the scale that we want. And via using mechanochemistry, we find that we can do that with a lot better precision than the corresponding liquid state processes. So specifically, we can make now chitosan between 20 and 200 kilodalton with really nice monodispersity. And we can do that with a process that, again, reduces the PMI by about an order of magnitude. Another thing that we're doing too is trying to functionalize the chitosan. And this is an interesting story because when we make this new functionality here, we can achieve results that are not feasible in the liquid state. And I can explain that to you a little bit. So what we're doing here is we're doing a coupling reactions where we are functionalizing here the amine by coupling it to an aldehyde and reducing it to form the secondary amine here. This is a very classic way that people have been functionalizing chitosan before. But it's not working really good because the problem is that to do that, you have to go through this intermediate. And in the liquid state, because of reasons I can explain more, the reaction is reverted to the starting material. But in mechanochemistry, because we don't need to change the pH to make this soluble, we can actually make this reaction quantitative to this intermediate and then reduce it to the final product with full efficacy so that we could make degree of substitution, which means how many of these functional groups here I add to my molecule, we can make it 100%. We can functionalize every one of them. And that's, again, something that no one's been able to do in the liquid state before. So mechanochemistry really gives you a lot of advantages, even from a chemistry standpoint. So we really try to work more with that. And one example is if we functionalize with this aldehyde here, we can make now chitosan soluble across all pHs, which is really interesting for applications. So this is where I wanted to sort of take you earlier. Chitin has this interesting property to be nanostructured. And what you can do from that is extract these nanomaterials called nanochitin. So these nanomaterials here. And some of you may know that because this is something that has been done a lot with cellulose. So cellulose and chitin are materials that have this nanostructuration. You can extract the nanochitin or the nanocellulose by using different acidic treatments or even oxidative treatments. It makes these materials that you see here, and these have been developed for a bunch of applications before, based on the fact that they have, that they have these types of properties. They can self-assemble. They're very strong. They're as strong as Kevlars, each individual whisker here. They can have photonic application. They interact with light. They have thixotropic properties too, because of the way they behave as gels. So there's lots of people who have developed them for making, for instance, aerogel. You can see here an example of an aerogel cellulose, or also for cosmetics. That's another example that people have been using. This is the use of nanocellulose for different applications in skincare. And yeah, and with nanochitin too, people are also working in this area. It's used a lot in Pickering emulsions. I know a lot of you are working in oil recovery. So Pickering emulsion is one of the mechanisms people are using for oil recovery. Nanochitin is a big player in this area. You can make as well liquid crystals and make different interesting materials that way. And there are also some applications for biomedical purposes too that we can talk about. So what we thought is that all of this chemistry has been developed in a number of ways in the nanoscale using liquid state chemistry. And one of the drawbacks of that is that the nanochitin that you make, they're very nice, but you would like to make nanochitosan because, again, I told you chitosan have these really nice properties. They're antibacterial, they're highly soluble. But this is not possible to do. It's difficult to do because of the fact that when you start to do the deacetylation, you lose the properties of, thank you so much, that's very good. You lose the property of the self-assembly here, and you lose the nano-whisker shape to make some, ill-defined materials. So we worked in this area in a number of ways. First, we demonstrated that we could make nanochitin. This is, by the way, the only liquid state process that I'm going to show today. Developing the synthesis of nanochitin, and then the synthesis of nanochitosan this time, where we retain the whisker shape here, which is essential for some of the properties that I've mentioned to you. So we do that by actually applying here some interesting chemistry where we're using sodium boryl hydride as a way to reduce the tips of these materials, to hold them together and hold them as whiskers. And we thought maybe we could use mechanochemistry to do that. And in fact, it's working even better. So when we use mechanochemistry, we can take nanochitin, turn it into nanochitosan, and preserving the nano-whisker shape. And at this time, we don't need to use any reducing agents. So again, in terms of chemistry, it's very simple, very lean, and we can preserve the structure of the nanomaterial really nicely. And this was really important because it helped us develop these hydrogels that are very simple, just based on the fact that we can mix together nanochitosan and alginate without any cross-linkers. And together they will form these gel structures that have really nice mechanical properties. And we could use them for different applications. And one of them is the use of the production of systems that can do drug delivery. So with these, we've been able to use a nanochitosan we made combined with alginates. Here we use a bovine serum albumin as an example of a drug. And we demonstrate we can do sustained release over a long period of time simply by making these gels, again, under very, very simple conditions. And I will finish with one last example, which is one where we are trying to apply these new nanochitosan for wound healing. So in this example, what we have developed is, again, taking advantage of the fact that now we have nanochitosan and they're present in the form of these nice whiskers. We thought maybe this would be an interesting material to tackle an important problem, which is how do we make Band-Aid stick to the wound? We all know that if you have a Band-Aid and we put it on some part where it moves, the Band-Aid is going to fall off, right? So what we want to do is we want to take our Band-Aid. Prior to putting the Band-Aid, you would put some material, in our case, the nanochitosan. Then you put some ultrasound. This helps the chitosan penetrate the skin a little bit. And then you put the Band-Aid on the top of it. And then you try to remove the Band-Aid, and you try to see how much force you need to remove the Band-Aid. That will tell you how sticky the Band-Aid is. So, by doing that, we discovered that using the nanochitosan that we used before, under some conditions, we have really an intense energy adhesion increase that we observe, which means that we cannot remove the Band-Aid very easily. You need a lot of energy to do that. And it works very well with different types of tissues that we find in the body. So this is something that you could imagine using for surgery or different applications. And then we looked into the binding between the Band-Aid and the nanochitosan, and we found that, oh my God, we're created a really nice network. So this is an example where we have no ultrasound, and you see that between the skin and the Band-Aid, there's really nothing. It's void. But when we have the ultrasound, now we have this dense network here. And you can see that a little bit clearer here. This is the Band-Aid. This is the network of nanokitasan, and this is the skin. And its structure as a network is quite unique to this material, and it allows us to have this really high adhesion energy. That means the Band-Aid is well stuck on it. Another property is that now what you want to do is remove the Band-Aid, try to stretch the Band-Aid multiple times. So this is like the equivalent of me doing this multiple times. We put Band-Aid on top of it. So, there's a little machine that does it 10,000 times. And we find that when it's stuck again with a nanokitasan, the Band-Aid remains in place. Whereas if we use regular chitosan, the Band-Aid would gradually start to tear apart. So that's because we have a mechanism crack thinning, and we're doing a lot of experiments to do that, but to demonstrate that. But the sort of take-home message for you is that with nanoclitasan now, we have a system that has both high energy and high fatigue resistance, what you can see here. And that's quite unique to all the other systems that people have developed before. So we're really excited about this. This is something that we want to continue doing. And we're really like started to look at the properties of these new materials. We're making some films with them. We're looking at their rheology. We're looking at different chemistries that we can do with them to modulate their properties. So we're really working a lot on this area. And overall, what I hope I have convinced you that we're trying to do, what I hope I convinced you today is that these materials are super interesting. Based on crustacean shells, we worked on processes to try to extract chitin and chitosan with better efficiencies. And now we're starting to do all sorts of chemistries around these materials to try to develop novel and advanced materials that we could use for a bunch of different applications, from biomedical to drug delivery to other areas that we're really excited to work with. So we started a lot of collaborations with people to look at these types of materials. And overall, what we find is that by replacing liquid state chemistry with solid state chemistry, we have better yields, lower chemical input, lower waste, high efficiency, high quality of the materials we make. And we are working on scale up. I showed you an example where we did that for the first process. We're going 10 kilogram right now. So these are the people that I have to thank. I want to thank Tony for his work on the nanomaterials. Faiza and Juliana worked on the chitin extraction. Galen worked on the chemistry of chitosan. Schwebing worked on the nanoadhesive. Madison made the library of materials that we're testing for films, and Hamda and Justina working on the scale-up. My collaborators, Vincent Bonville, Jeanne Mouly, and Edmond Lam, have been absolutely fantastic to work with. I also want to tell you that I'm also in charge of some electron microscopes that we do using for a bunch of applications. If you're interested in EELS, HADIF, EDAX, tomography for nanomaterials, let me know. We have all of that, and we want to use more samples. So we are really excited if you want to share samples with us to develop new techniques. I'm also the executive editor for ACS Sustainable Industrial Engineering. This is a journal that is publishing a lot in the field of green and sustainable chemistry. So if you want to submit your high-quality journal manuscript there, we really look forward to that. And I have to thank all of these wonderful people. This is us when we went apple picking 2 weeks ago. And lots of funding I'm really thankful for. And I want to thank you very much for your attention today. And I want to make one small comment, which is that we have developed a QR code for you guys to put to start answering the questions. What are your goals for the workshop, and what do you think is sustainability? And there's also sort of a wild card for you to ask questions and comments on the go. As you're watching presentations, if you have any thought, you're very welcome to answer them here. And the QR code is over here. So if you want to scan it and start entering the survey, that would be fantastic. Thank you so much.
Okay, thank you, Professor Audrey, for your presentation. Please round of applause for Professor Audrey. Okay, so maybe before going into the Q&A, maybe Q&A session first. Is there anyone would like to ask any questions to Audrey? Please. Yes. Okay, fine. Okay, we'll start there first. That's okay. Then, thank you. Your chance. Uh, I'm interested in your method, purchasing analytical science and mechanochemistry method. So, maybe I missed your presentation, but I want to know how you control the parameters to obtain the what is it, the molecular weight of the nanocrystal, and then how you make sure that the uniformity of the particle size of your nanocrystal, as well as is there any specific materials for the mineral itself uh, to make sure that the purity and yield of the nanocrystal can be if that's my question.
This is, thank you so much. I think that's fine. Yeah, thank you so much. No,
My name is Sona.
I think, no, thank you so much. This is a really super good question. Thank you so much. And it will hopefully help me clarify a few things. So let me just go back to this slide. Okay. So I have showed that we could use mechanochemistry to go from crustacean shells to chitin, and then chitin to chitosan. We do that by controlling the molecular weight to some extent. I don't think that we have a full control over everything, but we do have some control. In particular, what I can tell you is that when we go from chitin to chitosan, we use only very limited mechanochemistry and a lot of aging. And that is really critical for us because we think this is the way we can avoid some of the depolymerization of chitin that does happen invariably during this reaction. So we get higher molecular weight of chitosan because of the aging that we do in this process. Okay. When we are doing the functionalization here, the depolymerization or the functionalization of our chitosan, we also use a lot of aging because we believe that's also a mechanism by which we can combine the mechanochemical and the solid state reactivity with, on the other side, preservation of the molecular weight and the nanostructure inside the system by aging. Similarly, when you take nanochitin here and you transform it into nanochitosan by this method, we also use very mild mechanochemistry. In fact, in this process, we only use mortar and pestle, very gentle mixing and then aging in order to not damage the nanocrystals. So you're absolutely right that this is not, your question is right on point. This is not trivial at all. This is something that we thought a lot about and for which the developments, the combination of mechanochemistry with aging, we think is essential. So I didn't insist too much on this, but a lot of people use mechanochemistry, and I think it's working very well for a lot of processes. But in our hands, we found that in order to maintain both the molecular weight and also the nanocrystals, combining with aging has been critical for us in preserving the properties of the material that we wanted. Does that address your question? Great. We can talk more if you want. Thank you so much.
Thank you. Is there any other questions? Matt, you raised your hand. Yeah.
He's gonna grill me on the startup thing, so I'm worried now.
Don't be worried. It's fascinating chemistry. I guess my question is about, let's say, the larger scale mechanochemistry, which is how you collect the reagents at large scale. You know, you think of the thousands of restaurants where people are eating crabs and shrimp.
Yeah.
So how, like from an energetic perspective, it makes sense on a reaction level, but does it also make sense if you think about collecting all of this chitin shells from the thousands of restaurants where this is generated?
Yeah, I don't think my I don't think this is working super well. Yeah, so this is a great question. Thank you so much for asking. So we thought a lot about that because biomass, another issue with biomass that I didn't talk about earlier is that you transform a situation where you take a well that is here. I have a well and I'm going to pump oil and I don't need to move. I just pump oil. So I can build a plant here to treat the oil and everything is at the same place. Whereas you replace it with having to harvest this entire thing and then bringing it here and then foundation, right? So this is complicated. So fisheries is a little bit better because instead of having a two-dimensional field or two-dimensional forest, you typically have now one dimension, which is your coast. And in fact, I showed you earlier that in fact in the north coast of Quebec, you have harbors that are quite limited in their scale where you can harvest things. But then your next question is, okay, if I eat my lobster, where do I put my shell, right? So this is why we're not going to start with lobster, because lobster are typically indeed fish and then shipped to Asia or to the US for people to eat it, and it's shipped with the shell. But there's a lot of places where you process the meats on site and then have the shell there. So this is where we want to start. And in fact, all the numbers I showed you earlier for the crab operation is because in the North Coast, they process the crab, they process the meat, and they have the shell right there. So these are real numbers of what is there to be used tomorrow morning. So this is what we're starting here. But yeah, I don't know if it will ever make sense to collect whatever is in the garbage of people or in restaurants, maybe in large restaurants that are really doing a lot of crustacean that will make sense. I don't know. But we're starting with food processing because we think that this is where we have a handle over large enough quantities. Did that answer your question? Okay, good. Okay.
Okay, so starting from the large industry first, and then we start from there to make it business feasible, maybe, and then we continue to the smaller groups. So
potentially, if it ever makes sense, but starting like in business, you want to start with it's so complicated. You want to start with the place where you have the highest chance of it working, because otherwise you can. It's too difficult.
The volume speaks.
Exactly,
right?
the volume is
sure. Okay. Any other questions, maybe? From the audience and participants? Okay. This is like a dissertation.
I had a question regarding your beads for production, the blend between chitin and protein.
Yeah.
And what the proportion was, and because thinking about those two products, there's like a lot of potential for industrials to you can harvest quality or to harvest.
Yeah, exactly. I can't remember from the top of my head. I'll have to look back at the paper, but it's pretty like 1-to-1 kind of thing. So I don't think there's a large excess of one or the other because you need the cross-link to happen. So yeah, I'd have to go back to the paper to give you the exact number, but it's pretty good. Yeah, I think everybody wants to have lunch now. Yeah, exactly.
Okay, no worries. So maybe I'd like to wrap up your
you
talk
so much.
for today. So again, this is a good example from Prof. Audrey. So Prof. Audrey and her team are conducting a mechanochemistry study, which is a mechanical course implemented to enable chemical synthesis. And you've also, so from biomass, synthetic catalysis, and assessment metrics, you've conducted. So the point of biomass energy from biomass is from food waste. So not from the first production of from the agriculture. So from food waste itself. And Prof. Audrey have given example of from fishery waste, right? So from fishery waste, this is sustainable use of marine source. And she's taking example from crustacea, which we can produce from waste of crab, shrimp, and lobster. And also like it's already conducted there in Canada and also Indonesia. I think there's a lot of prospect because we eat a lot of seafood, right? So of course we can use this and produce chitin. And from Audrey said that producing chitin and combining it with protein and mineral It can be complicated and costly, but again, remember guys, because it doesn't stop us from previous endeavor to make a better place, to produce from waste and to make it something useful again for our society. And uh, also from the study itself, she also pointed out from the mechanochemistry, her team substitute from Band-Aid with cytosine. So as nano adhesion, if I'm not mistaken,
nano
adhesion. So, and from the research itself, you can produce a higher molecular weight combining with aging solvents to maintain the structure. And from the point of view in business, of course, collecting crustacean, because from research and from economic point of view, we have to start from a large industry first, and then from there, maybe we can, if that succeeded, we can move forward to creating the supply chain and also regulating the waste of crustacea. Is that okay?
Yeah. No,
Okay.
I want to thank you because you wrote a beautiful summary of
Thank
my
you.
talk.
I'll
Thank
try my
you so
best.
much.
Yeah. Thank you very much.
Congratulations.
Yes, thank you. Okay. Thank you again, Audrey, for your
Thank you.
presentation.
Thank you so
It's
much.
very insightful, especially myself also because I have no background in chemistry again. But from this, we have a lot of produced waste, right? So we have to make something out of it, and it can be also useful for us. Okay, thank you, ladies and gentlemen, and thank you, Audrey, for your presentation. We will continue.